Hey, Calculus, this is the second part to Section 5.4, all about the fundamental theorem of calculus. So again, feel free to pause, take a little break if you need to, jot down any notes or extra notes or questions that you might have, rewatch anything that doesn't make a whole lot of sense, and let's get rolling here. The first part, the first part we've already talked about, but the second part of this fundamental theorem of calculus says that what we're really kind of focused on is the fact that if you're going to take an integral and evaluate it from A to B, so a beginning point at A and an ending point at B of whatever your function is, you can just essentially apply it as the antiderivative at B. So find out what the antiderivative of the function is and evaluate it at the specific location of B. And then subtract the antiderivative at point A. So again, you've got that antiderivative function. You substitute in the lower limit part A, and you subtract those two values. And that's going to be your full out integral, what we have right here. Okay. This is also called to help you out, the integral evaluation theorem. Integral evaluation theorem. And there's a nice little proof that goes along with it. You can say, hey, let the antiderivative of g equal the derivative from a to x of the function f of t dt. We talked about that the other day in class. And we kind of go through all the different steps as to how that all unfolds. You can copy this down if you want to. You can kind of read through it. It's not that big of a deal. It's a great proof. It kind of paves the way for what we can explore down the road here. All right. But essentially what we're really doing is we're letting the antiderivatives, all right, equal those integrals. And what they end up doing here, and you kind of see that the constants right there will subtract out. So you don't have to worry about that constant at all. And we'll just end up with our lower limit and our upper limit that we can subtract. All right. So that's the proof. It's a nice proof right there. Feel free to rewatch that and look over it and write it down if you want to. It's not necessary though. All right, evaluating the integral. We're going to apply that fundamental theorem of calculus right here, and we're going to go from -1 to +3. All right, from -1 to +3, we've got our function x cubed plus 1. So maybe the first thing is find the antiderivative. Find the antiderivative of x cubed plus 1. So if you're at x cubed, you got to remember, okay, I got to go one exponent larger than what I'm at. So I really want to be at x to the power of 4, because if I take the derivative of x to the 4th, I'll get x cubed. But look at my coefficient. I want my coefficient to be 1. So if I take that 4 and multiply it down there, I'll end up with 4x cubed. And I don't want that. I want 1x cubed. So I got to make my coefficient, let's see here, 4 times something equals 1. Well, 4 times 1/4 equals 1. So that would be 1/4 x to the 4th. All right. If you do a quick test here with your derivative, if you take that 4 and move it down to the coefficient, that would be 4 times 1/4, and then subtract 1. That would be 1x to the 3rd. All right, so that little test right there ends up working out for us. The other part of this is that plus 1. Well, that doesn't have an x, so I'm gonna make sure I add one more to the exponent there, so it's going to be x to the 1st. And if I take the derivative of x to the 1st, I just get out 1, so I know I don't have to worry about any coefficients or anything in that manner. So that's my my antiderivative. I could put plus c, plus a constant on there, but I know the constant disappears. So I don't need it. All right, I'm going to evaluate this from -1 to +3. From -1 to +3. So the rule that I just looked at, the fundamental theorem of calculus there, I can say this is going to be the antiderivative at the upper limit minus the antiderivative at the lower limit. All right, so let's take a look at the first part. I have to substitute 3 into my antiderivative. So that's really going to be a 1/4 times by 3 raised to the power of 4 plus another 3 minus, now I have to do the other part, the red part there, the antiderivative at -1. So I have to substitute -1 into my antiderivative formula. So that's going to be a 1/4 times by -1 to the power of 4 plus a -1. Okay, well, I can clean this up a little bit. I've got, let's see here, 1/4 times 3 to the power of 4. 3 to the 4th is 81. So I've got 81 over 4 plus 3. If I get a common denominator there, that's going to be over 4. So it's going to be plus 12 over 4. So that'll end up being a 93 over 4. All right, the red part over here, I've got negative 1 to the power of 4 is going to be a positive 1. So positive 1 times 1/4 is just 1/4. And then I've got, let's see here, a plus a negative 1, so it's just minus a 1. Maybe get common denominator right there, a 4, so minus 4/4. So that'll end up being a green part 93/4, the red part negative 3/4. And remember, I want to subtract that. So subtract those two. All right, I'll turn that into a subtraction. Negative is really addition of a positive. We got 93/4 plus 3/4. That's going to be a 96/4. And that cleans up to just be a plain old 24. All right, so that value of that integral is actually 24. And if you want to apply this and say, okay, does that mean that the area that's underneath that curve from the x value of negative 1 to the x value of 3 is 24? It sure is. All right, let's try another one here. How about one with trig? Evaluate from 0 to pi of 1 plus the sine of x. So again, we start off by trying to figure out what is the antiderivative of 1 plus sine x. So what function gives you a derivative of 1 plus sine x? All right, well, what function gives you a derivative of 1? That would be x. And then what function gives you a derivative of sine x? All right, not what is the derivative of sine, what function gives you a derivative of sine x? Well, that would be a negative cosine of x. And we want to apply this from 0 to pi. All right, so that's our antiderivative. We actually go through those steps there, and we can say to evaluate this with the fundamental theorem of calculus, we're going to figure out the antiderivative at the upper limit minus the antiderivative at the lower limit. All right, so then the green part right there, the antiderivative of the upper limit, that's going to be substitute pi in for x. So that's going to be pi plus a negative cosine of pi. All right, minus the red part, substitute 0 in for x. That's going to be a 0 plus opposite of cosine of 0. All right, so we clean this up a little bit here. The green part, let's see here, pi, that's going to stay put as pi. That's not going to change. You've got a cosine of pi. So you can go back to your rules of trigonometry. You can do a little rough here of a cosine graph. Cosine graph starts at the tippy top, kind of goes down there. Pi would be right there in the middle. All right, so right there in the middle, you're down here at -1. But we're going to subtract that. So it's really going to be the opposite of a -1. So it's going to be a +1. So it's going to be pi plus 1 is the green part. All right. How about the red part? 0 is going to stay put as 0. That's not red. That's green. Let's change the color there. Now we have red. 0 stays put as 0. And then the cosine of 0, the opposite of the cosine of 0. The cosine of 0 is up here at 1. The opposite of that's going to be a -1. So that's really going to be minus a 1 right there. Okay, remember I got a big old minus sign between those two. So that minus sign, I'm going to make sure I can distribute that, or I could also say, hey, 0 minus 1 is just a -1. I can combine those like terms. So I'm really going to take pi plus 1 minus a -1 is really pi, let's see here, plus 1, which is just pi plus 2. And you can get a decimal approximation there if you really, really wanted to, or just leave it alone as pi plus 2. So that's kind of how we do that. It's pretty neat stuff. All right. How about an area connection? There's two different ways we can look at area. And we've been talking about integrals being, hey, it's just an area. All it is the area that's bounded between the curve or the graph or the function and the x-axis. Well, area really has two different kind of ideas here. There's an idea of what's called net area, which is exactly what we have talked about. All right, where if we say above the x-axis, we're going to have a positive area. Whereas if we have below the x-axis, we'll have negative area. Anything that's above is positive, anything that's below is negative, add them together and you figure out what you have. That's what net area is. That's what we've been kind of working with. There's another thing called total area. Total area is kind of just regular old area, kind of geometrically speaking. Total area, we're going to say all area must be positive. And what I mean by that is, don't just look at the positive area, because you still want to use the area that's below, that's underneath the curve. But if it is going to be a negative area per se, make it positive. That's what it means. All area is going to be positive. So there's a way to do that, and there's a couple different ways that we'll take a look at here. But that's what we're kind of focused on here. First question there, find the area of that. Notice it says area. It doesn't say find the net area, find the total area. It says find the area. Just some rules to kind of help us out. If they ever tell us to find the area, we're going to say that's going to be the total area. All right? That really means the total area. If they don't say anything about area, if they just say find the integral, all right, the integral, that's the net area. That's the blue part. So if they add that special word in their area, we're going to call that the green part, where it's just the total area. Everything's going to be positive. If they don't put that in there, they find the integral. That's what's called the net area. All right. So we're looking for the total area. Total area from 0 to 3. And I've got a little drawing here to help us out. And you can kind of see, hey, you've got you got a positive area that's going to be kind of up here. But then you also have a negative area that's going to be kind of down here. And we don't want any negatives. We only want positives. So essentially what we have to do is kind of flip this upside down. We want to move this up here to make it a positive area. All right. And there's a couple different ways to go about doing that. The first way that we'll kind of focus on is just figure out, well, where does it switch? Where does it switch to being positive to negative? And it switches over right there at 2. Switches over right there at 2. So if I kind of adjust my integral a little bit, I can say, let's find the integral from 0 to 2 of 4 minus x squared. All right. And that will give me all nothing but positive, because that's all above. So that's great. And then I also know I could kind of break this up to be, how about the integral to 3 of 4 minus x squared? Kind of like that. Well, that's only going to be the negative part. That's only going to be the part that's below. So I know my answer in that second part is all going to be negative. And I don't want it to be negative. I want it to be positive. So what I'll do is, instead of adding those two together, I'll just subtract them. I'll just subtract that second one, because I know my answer is going to be negative, but I want it to be positive. So that's one approach that I could do. All right, that's one approach. I would maybe try to figure out, well, what's the antiderivative to begin with? Well, 4, I need to add on an x in there, so that's just going to be x. All right, but I want to make sure the derivative of that is going to be 4, so I want to make that a coefficient of 4. So that's 4x, derivative of 4x is 4. All right, minus x squared. So I'm going to subtract x, and I want to add that exponent by 1, because x cubed, the derivative goes to x squared. But I don't want the coefficient to be 3. I want the coefficient to be 1. So my coefficient that I have to start out with is 1/3, because 3 times by 1/3 gives me that coefficient of 1 at the end. All right, so that's the antiderivative that I'm looking at. For the first part, I want to evaluate it from 2 to 0, from 0 to 2. All right, from 0 to 2. So if I do that, I'm going to try to figure out the antiderivative at 2 minus the antiderivative at 0. So I'm just going to take 2 and substitute it in for x. So that would be a 4 times by 2. All right, minus a 1/3 times by 2 cubed. Put that all in brackets maybe, minus the antiderivative at 0. That's going to be a 4 times by 0 minus a 1/3 times by 0 cubed. Okay, I'll clean all that up. I'll multiply it all out. All right, and I end up with a 16/3 minus a 0, just like that. Second part. All right, I'm going to make sure I subtract. I'm going to continue bringing that subtraction down. Just kind of, I realize that, and I'm going to tackle this other part right here. The second derivative, or the second integral, from 2 to 3. All right. So that's really going to be the antiderivative at 3 minus the antiderivative at 2. So really, I've got antiderivative at 3. Well, that'll be a 4 times by 3 to the power of 3 minus antiderivative at 2. I kind of already did that. That was over here. That's a 4 times by a 2 minus a 1/3, run out of space here, minus a 1/3 times by a 2 cubed, kind of like that. All right, I go ahead and clean all that up. All right, so I've got the antiderivative at 3, antiderivative value right there of just plain old 3 actually. And then the antiderivative at 2, I've already figured that out, that was 16/3, so I'm going to subtract 16/3. But remember, I have this sign that I'm going to continue down. So I've got to take the entire gray section minus the entire green section. All right. Okay, so if I clean this up a little bit more, the first up 16/3 minus 0, the gray section, that's just 16/3. Minus, if I clean up the stuff that's in the brackets right there, 3 minus 16/3. All right, 3 minus 16/3, that's just going to give me a negative 7/3. And notice that's a negative 7/3. Of course it is, because it's below the x-axis. It's a negative value. That's why I'm subtracting it, to really turn it into an addition. So subtracting a negative is really adding a positive. 16/3 plus 7/3 is going to equate to 23/3. So that's one way to do it. Figure out all of the negatives and subtract the negatives to make them really positives. Another way to go about doing this, is if you take your function itself, take that function itself, that 4 minus x squared, and rename the function. Ooh, you can do that? Yeah, let's rename it. We're going to say it's the integral from 0 to 3 of the absolute value of 4 minus x squared with respect to x. So make it the absolute value of the function. And what that does is all the y values become positive. Poof, just like that. All those y values will always be positive, so everything will be above the x-axis. All right, so that's kind of a nice little trick to kind of help you out with that. And we'll explore more with that as we progress further. All right, one more final thing here, using some technology to help us out. The difference between the net area and the total area of this one right here, and use the technology. Yeah, this one's going to be kind of a pain to take the integral of and find the antiderivative, but we'll use some technology to help us out. All right, and what we'll do here is, if we want to try to find maybe to begin with the net area, the actual integral. All right, the net area right there. If we use our calculator, all right, we use the calculator and we go over here. Remember, with the calculator, we can go to alpha F2. And let's see here, my fourth option down is the integral. So I'll go with that. And I want to type in the lower limit there, -3. Upper limit's going to be +3. My function itself is going to be x times by the cosine of 2x. All right, and I want this with respect to x. Before I calculate this, I'm going to make sure I'm in radian mode. So if you are out of that, make sure you're in it. I'm in radian mode, so that's good. So I can quit out of that. And I can go ahead and equate this right here. And it gives me a value of 0. That's kind of weird. So the net area is actually equal to 0. Okay, so that's really a 0. So what that means is we've got the same amount above as we have below. Let me show you one other thing that might help you out here. Of this function, that's kind of weird to kind of address and to kind of see, of this function right here. If we take a look at that right there, I've got it graphed. All right, x cosine 2x from -3 to +3. You can see it's very symmetrical. It's got that rotation symmetry. So it looks like it's an odd function. So you got the same amount above as you have below. Oh, okay, you got this little tiny section there, little tiny section there. They balance each other out. You got this big mountain here, and you got this big valley there. They're going to balance each other out. And then you kind of see where it ends at 3 and starts at -3. They also cancel each other out. So that's how that one works. All right, the other part of this is if we wanted the total area. Total area might be, let's change this around to be the integral from -3 to +3 of the absolute value of x cosine 2x. That right there means everything's going to be above the x-axis right there. So I can take a look at what that graph looks like, and I'm going to use Desmos to kind of give me that graph picture. Remember what the original one was. So anything that's below the x-axis is now going to be above it. So if I turn that one Oh, and you kind of see in blue, that's what happens. Those red guys that were underneath are now above. And I'll turn the red one off so you kind of see everything's up there. So everything's going to be a positive area no matter what. All right. So that's what I could use on my calculator as well. I can go back over here to the TI calculator, and I'm gonna do the exact same thing. I'll go back to alpha F2. I'll go over to the integral button, number 4. I'm going to go from -3. I'll go on up to +3. All right. But this time I want the absolute value. So to find the absolute value, I go over to the math menu over here. And in the math menu, I go over to number. And the first option there says absolute value. All right. The newer calculators put the absolute value bars in. The older ones just say ABS and open up a parenthesis. It does the same thing. All right. I'm going to type in the function as it was. So x times by the cosine of 2x. All right. Close the parentheses there. And I can go over here and say this is with respect to x. All right, and I can equate this one, and this one takes some time. It's thinking. This was a hard integral to figure out. So the calculator's working, it's doing its magic, and it's coming up with an answer. And yours is probably going just as slow as mine is because it's a really, really tough integral to figure out right there. So it's coming up with its value, and as it kind of finishes up, you'll see exactly kind of what the answer is to kind of realize. You know, it's taken a long time right there, but I got hopefully yours is finished by now. I got about 5.42. It should be popping up any moment now, but about 5.42 and so on and so on. 5.4250. There it is. All right. So that's the value that I got. Notice it's positive. It should be. Everything is above the x-axis. So that's the answer for the total area. All right, so I got somewhere around 5.42. All right, so that's how you can use your graphing calculator to help you out. If you've got one of those awesome Casios, I'll be more than happy to give you some more pointers with that one as well. If you need to, just ask or shoot me an email, and I'll give you some resources to help you out with that. All right. Other than that, again, if you have any questions, write them down for me. Let me know. Do your best. Rewatch anything you need to, and we'll keep practicing. I'll see you next time. Have a nice day, everybody.